Okay, thank you very much. Many thanks to the organizers for giving me this opportunity to present some problems. So the title is some analysis of quantum Boolean function, which I will explain what they are. I chose this title because I specify two topics, and I don't know which one suits people here best. But both of them fall into this picture of analysis of Boolean functions. By the way, if there is no quantum here, this is the title of a very well-known textbook where you can find the relative background. This is a book by this is a textbook that you can find some more. Okay, I think yeah, maybe this one. Yeah. Oh, sorry. Yeah. Anyway, we want to put quantum here, and there are a lot of problems in this program, and I want to focus on those with potential applications. Okay, so the plan is as follows. I don't assume you know anything about this type of analysis of Boolean functions. So I will start with some basic notations. After that, I will formulate the problems in the classical setting, give you a flavor how they look like, what kind of reanalysis tools that we use, and then we decide which problem to discuss, okay, in the quantum setting. So throughout, I will fix this little n to be a positive integer. I will explain to you what these Boolean functions and application look like in the classical and the quantum setting. So maybe let me give you a comparison. Here in the classical setting, we will consider a function defined on the n-dimensional Boolean cube. In dimension 1, this is just a two-point space, or this is just a cyclic group of order 2. Here I choose a multiplicative cyclic group, where you can also take 0, 1 if you want. And if you consider general analysis problems, you can consider real value, complex value, or sometimes vector values if you are interested in the geometry of Banach spaces. In the quantum setting, we will replace this by by 2 to the n by 2 to the n matrices. So throughout, K will denote the class of all k by k complex matrices. Okay, is the handwriting visible, or is my voice clear? Okay. Then, what are the Boolean functions? Boolean functions are the ones which take values only in +1, -1. So these are the Boolean functions. Again, you can also take the definition to be function that take values in 0 or 1 if you want. In the quantum setting, you can easily generalize this to the following. You say this matrix A, that is of size 2 to the n by 2 to the n, is said to be Boolean if it is self-adjoint unitary. This definition is due to Montanaro and Osborne, which mathematically is very reasonable, right? If you consider a function that takes values in plus minus 1. If you consider a function that takes values in 0 or 1s, maybe you should replace this by self-adjoint projection.
You don't mean the interval, right? I mean, you just...
Yes. So, yes. So please stop me if you have any questions, okay? Okay, before giving some examples, let me first recall the free expansion. Which can be defined for any functions, okay? Not just for Boolean ones. Here I will write the free expansion as follows. Okay, we know that any function on the n-dimensional Boolean cube is a linear combination, unilinear combination of the characters of the group. Here I use this chi-s to denote this character. What is this s? S here is a subset. Is a subset of first n positive integers. Then for each chi-s, it is defined to be the product of the coordinates xj, where j belongs to this set of S. Okay? So, in other words, any function on the n-dimensional Boolean cube is a very special class of polynomials. These are multivariate polynomials in n variables, and it only consists of the multilinear ones or multi-affine ones. You don't have a square term. Square term is always equal to 1. Is that clear? Because xj takes values only in plus minus 1. Okay. And this is a free expansion. In the quantum setting, we have a similar expansion, sometimes called Pauli expansion, because we have the Pauli matrix. Pauli matrix is at the basis of the 2x2 matrix algebras, which I denoted by sigma naught, which is identity. Then for the rest of the three, I denoted by sigma 1, sigma 2, and sigma 3. Check if I'm correct. Anyway, I will use sigma naught to denote an identity. For the rest of the three Pauli matrices, only thing that we need to know is that they satisfy this anti-commutation relation. Sigma I, sigma j is sigma j, sigma I with negative sign. When I and j are different, ranging from 1 to 3. In particular, for each sigma I, we also have that sigma I itself is the self-adjoint unitary. So sigma I square is equal to identity. Okay, so this is the basis of the 2x2 matrix algebras, and I'm going to use their tensor product to form my free expansion or Pauli expansion. So my matrix A here is always linear combination of the following, where this sigma s vector, this s vector here is an n-dimensional vector with each entry being 0, 1, 2, 3, and the definition is simply all these sigma sj's. Okay, so here it is indexed by this n-dimensional vector. Each entry is 0, 1, 2, 3, telling me which Pauli matrices I'm using here. That is my basis, and this A hat of S vector is some complex number the Pauli coefficient or the Freire coefficient.
Can you write the formula for a part of this?
This one?
Mm-hmm.
That will be the next step. We are going to, yes, so I guess Adam's question is whether they form an orthonormal basis so that you can recover the Freire coefficient. And the answer is yes. In this case, we equip so the probability measure here on the classical Boolean cube is essentially this uniform probability measure. So for in the one-dimensional setting, you have 2 points, and they have equal probability 1/2. So it is 1/2 delta plus 1 plus 1/2 delta -1. Then you form the n-fold product. That is your uniform probability measure in the n-dimensional discrete hypercube. As a consequence, you can easily check that this form orthonormal basis, the Ks here form an orthonormal basis with respect to this uniform probability measure. So we have the Hasselbalch identity saying that the little L2 norm of my Freire coefficients, okay, so this is a little LP norm. This is a little LP norm. Well, on the right-hand side, I have the LP norm defined with respect to this uniform probability measure. This is how I define my LP norm of my function with respect to the uniform probability measure, so that I have this Hasselbalch identity, and if you want to recover the Freire coefficient, it is given by the inner product of your function f and the character Ks with respect to the inner product induced by this uniform probability measure. Okay, in other words, the form orthonormal basis, and we have the same thing here in the quantum setting if we replace this uniform probability measure by the normalized trace. Okay, so this trace has no normalization, this is the Euro trace without normalization. With this normalization factor, the identity matrix will have trace 1. Okay, with respect to which you have Hasselbalch identity. Little L2 norm of a Freire coefficient, which is again a sequence of numbers. On the right-hand side, you have this L2 norm defined with respect to this uniform, with this normalized trace. Then if you want to recover your Freire coefficient, it is again the inner product of your matrix A and this basis sigma S vector with respect to the inner product induced by this normalized trace. Okay?
I'm just thinking, so when you compute the L2 norm of A hat.
Yeah. This is again little L2 norm. Mm-hmm. Any other questions? Okay, so one thing that I have not mentioned to you, so in this analysis of Boolean functions, the general picture, okay, one general picture that you can keep in mind is the following. We want to have a better understanding of Boolean functions. Whose definition looks simple, but sometimes can be very much involved. We want to have a better understanding of the Boolean function, which in general is not easy. So we want to understand those with small complexity. Which I will define later, okay? There are many different ways to measure the complexity of this Boolean function. So when this complexity is small, you may expect the Boolean function have a better structure, okay? So understand the structure of the Boolean function with small complexity. That is the general goal. And this usually leads to some interesting applications, which will be the focus of today's presentation. Okay, any questions so far? Let me give you some examples. Examples. Okay, is this visible to everyone? Okay, so a very simple example of classical Boolean function is so-called the dictatorship. By the way, these examples and many motivation of the Boolean function come from the social choice theory or voting theory. So here, this dictatorship it means the whole election or everything is dominated by a single person, the jth person. So this is certainly a very simple Boolean functions. Next one is the majority. So if more than 1/2 of the people agreed in the sense that, okay, more than 1/2 of the coordinates is +1, then the output is +1. Otherwise, the output is -1. So this is a majority function. So you can see that the definition of these two examples are very simple. But very often you need to understand the function from two different worlds. You understand the function from the very definition, point-wise how it looks like. But you also want to understand its Fourier transform. You want to understand the spectrum, Fourier spectrum of this function, which is not so easy, okay? If you want to compute the Fourier coefficient of these majorities, it's not so clear, not like this dictatorship. Okay? Another function that I want to mention here is generalizations of dictatorships. Dictatorship depends on only one variable. If everything is governed by at most k people, so if a function essentially depends on at most k variables with k independent of n, k here, independent of dimension n here, then we also understand this function to be simple. In other words, we regard this family of, the dictatorship and the juntas to be Boolean function with a small complexity. This is one way of measuring this complexity. I will give you two more complexity measures, which will be the main focus today. But before that, let me give you some quantum examples. Although the definition is very clear, you just find self-adjoint unitary, then that will be a quantum Boolean function. That is one example. But actually, there is a huge difference between the classical setting and the quantum setting. So let's try to do the following thing. If you represent this function in terms of Pauli expansion here, when does this become a self-adjoint unitary? Let's consider the following example. Don't know if you can read this part. So here is just a 4x4 matrix with m being 2, okay? You have A that is linear combination of these two very special bases, sigma naught tensor sigma 1, sigma 2 tensor sigma 3, okay? Then you have the coefficients alpha and beta here, then when this is a self-adjoint unitary. Okay, then clearly alpha and beta here, you can assume it to be real. Then let's compute when it is a unitary. A square here is going to be alpha square. Okay, so each of these tensor is itself the unitary, plus beta square. Then you have two cross terms, plus alpha beta. Then when you compute, you have two terms. Firstly, the first one multiply the second tensor product. Sigma naught is just identity. So here you have sigma 2 tensor sigma 1, sigma 3. And the other way around, you still have sigma 2 here. So let's write this sigma 2 here as a common factor. Then the rest just the sigma 1, sigma 3. Plus sigma 3, sigma 1. Okay, because this is just identity. Now something non-commutative happens because of anti-commutation relation. Sigma 1 tensor sigma 3. Sigma 1, sigma 3 is equal to negative sigma 3, sigma 1. So this part is vanishing, and you are left with alpha square plus beta square times identity. So you know that this is a self-adjoint unitary or quantum Boolean function if r square plus beta square is equal to 1. Alpha, beta are any real numbers between 0 and 1. So this is a very simple calculation, but this is a very strange phenomenon because this will never happen in the classical setting. What I'm saying is that if you consider a classical Boolean function, you have a very simple structure, which means, say, your degree is finite, is bounded. Then you can never have real coefficients that have this kind of flexibility. It can be any real number between 0 and 1. But in the classical setting, this is not the case. This is not the case. In some sense, your Fourier spectrum here is kind of discrete. It must be some integral multiple of some 2 to the power 1 minus d. But here it is continuous. And this phenomenon is...
why can't I let alpha and beta be negative?
Yes, you are right. They can be negative. So, yes, they can be negative. You are right. Thank you. Okay, yes, they can be negative. This is not an even only. If you want to even only, yes, it can be negative. Yeah, you're right. So okay, maybe let me mention here that if you have a Boolean function, okay, maybe it's better to make this remark later. If you are really interested in this problem, we will come back to this. So these are some very simple examples of classical Boolean functions and quantum Boolean functions. We will see later, if we have time, why this is a very bad news. Now let me come back to this problem. We want to understand Boolean function with small complexity, and we will focus on two complexity measures. Maybe let me put it here. The first one is a notion of degree. whose definition is kind of clear in the class setting, because your function is always some multivariate polynomial. Just define the degree to be the degree of the polynomial. So say that degree of this function f, which is not necessarily Boolean, is the maximum of the cardinality of the set capital S whenever its corresponding Fourier coefficient does not vanish. So here this so this denotes the set of the cardinality of this set. This set is a subset of the first n positive integers. Okay, this is just define the degree as a degree of a multivariate polynomial. And in the quantum setting, in the QP system, I will define it to be in a similar way. This time I regard this matrix A as a non-commutative polynomial in the sense that I consider this tensor product as some polynomial. Then what I really care if is in this tensor product, do I have identity or not? If I have identity, it means it has no action on the corresponding qubit system. If I have sim 1 to 3, it means that I have really non-trivial operations. So in this sense, I define the degree to be the maximum of the length of this vector S, where the Fourier coefficient does not vanish. And the length of this vector is defined to be the cardinality of the non-zero entries. Okay. As long as it is not identity matrix, it will contribute to the definition of the degree here. For example, for this polynomial, if you look at the first part, it is of degree 1. If you look at the second part, it's of degree 2. Is that clear? So the first subproblem is what can we say for Boolean functions in both settings when this degree here is very small? That is the first problem. Second notion of complexity here is the so-called influence. How do you define the influence? This time I first fix some coordinate I. I want to look at the influence of the ith variable to your function Cf. Here, let me remark that in defining degree here, I don't need the function to be Boolean. Here, let me fix the function to be Boolean. Okay, influence for Boolean functions. You first fix a coordinate, then the ith influence, the influence of the ith variable of your function f that is fixed here is defined to be the probability that f changes value when flipping the ith variable. Here I have this notation x flip I, which means I fix I flip the ith variable from xi to negative I while keeping the rest of n-1 coordinates unchanged. Okay, I just flip the ith variable, maybe from +1 to -1 or from -1 to +1, without changing the rest n-1 coordinates, then I look at how much this influence, what it would be the influence for my function here. So this is a probability with respect to uniform probability measure. Then you look at the probability that f changes value when flipping the ith variable. Okay. This is kind of the very definition, but you can interpret it, this definition in many different ways. This is also equal to the following. If you use a partial derivative operator, which I denote by capital DI here, this might be used frequently, so let me define here DI of f is f of x minus fx flip I. Okay, it's kind of the discrete analog of partial derivative along the s direction. You can also think of this as you equip this plus minus 1 to the n as a graph. Then at the point x, you look at the ith direction, and you measure the difference in the next step. If you flip the ith variable, you kind of jump to one of the neighbors in the ith direction. Then this is the definition of DI here. It is a naive calculation that this definition of influence can be rewritten as is square of the L2 norm of DI of f, okay? Because the function just takes values in plus minus 1. It's different if and only if one of the negative one, the other one is plus 1, so the difference, the average here is actually 1. So it's a naive calculation, and this naive calculation also tells you that this is equal to the piece power of the LP norm, no matter which p you choose. The reason is very simple. When your function is Boolean, then this DI of f will take the values 0, plus 1, minus 1, nothing else. So naively, it's always piece power LP norm. You may ask why we have these different representations. They are actually very crucial in proving the theorem that we will discuss later. Of particular interest is this case when p is equal to 2 because of the partial identity or because of orthogonality. In other words, you can also represent this influence in terms of Fourier coefficients. Then this will be sum of squares of the Fourier coefficient at S, where S contains this I. Okay, S contains this I. So in particular, if the ith influence is equal to 0, it means your function does not depend on the ith variable. So when this quantity is small, it means the dependence is very, very weak. Okay. Before going to the next definition, let me remark that this property fails. This property fails in the quantum setting. Just look at this very simple example. Just look at this simple example, but maybe I should first define the quantum influence. Okay, so let me Let me first try to mimic the definition of influence here in the quantum setting. I still fix my s variable, and I want to define the influence of this matrix A. But now it is not so clear of these point-wise definitions, especially this property that di of f takes values in 0, 1, and -1. This is no longer true anymore. So defining influence itself is not so, it's a bit tricky. We are going to take this LP norm definition as a starting point. So this time it will depend on P, unfortunately. Fix P to be any number bigger than or equal to 1. Then with respect to P, the I's influence of this matrix A is defined to be the I of A, P's power of LP norm di of A. Again, this LP norm is with respect to the normalized trace. What is this di? Di here is di here, this little di here kind of mimic the capital Di in the class setting, some kind of discrete partial derivatives. In other words, in the i's variable, it acts as identity minus the normalized trace, while in the other -1 coordinates, it's just identity. So why this is equal to the classical setting? In defining this capital Di here, di of f is f minus f flip xi, while this is also equal to f of x minus average of f of x and f of x flip I. Okay, so in the i's variable, just take the conditional expectation, or you take the average over the i's coordinates. You subtract this by the original value of f. This is the same of this capital Di. And this definition, little di here, kind of mimic this capital Di. This is a quantum bit flip map. With this, you can define the influence here for any p. And the point is, in general, they can be different. Of a particular interest is when p is equal to 1 and p is equal to 2, then the corresponding two notions of influence do not agree. Yes?
So does these non-commutative derivative matrix derivatives, this also gives you a notion of monotone?
This is a very good question. Asking monotone Boolean function, right?
Well, monotone
quantum Boolean function. I see only one definition of monotone quantum Boolean functions. Maybe we'll come back to that later if we want to discuss the monotone graph property or monotone Boolean function. So that might be too far away, but maybe we'll come back to this notion of monotonicity. Okay, to see that why this can be different, just look at, again, this very simple example. Let's calculate, for example, d1 of A. What does this mean? When you look at d1 of A, it means that you will essentially trace out the first coordinates if it is equal to identity. Okay, so the operation is that in the first coordinate, you act as identity minus normalized trace. Okay, so for identity matrix, this becomes 0. If it is not identity, polymatrix has sim 1, 2, 3 has trace 0, so it will remain unchanged. So the only survivable term is the second one, which is beta sigma 2 times sigma 3. So it is some multiple of a unitary matrix. Therefore, is LP norm, P's power of the LP norm is always equal to beta to the power of p if beta is positive, by the way, if beta is positive or absolute value. And this certainly will not agree for p being 1 and p equal to 2. And this crucial property, okay, even this example shows that the worst scenario, that L1 norm and L2 norm can even agree. They can be the same. And this is in some sense the worst thing that we want to see, but it happens in the quantum setting. Okay. Any questions?
One question. So you said that you want to view both of these,
yeah,
degree and influence, as measures
yeah,
of complexity.
Yeah.
So is there a nice way to combine influences at the kind of, if you define the influence of a given variable?
Yeah.
So how do you combine it? Is it
I'm asking relating the influence and the degree in some way, or
what's total influence? What's the right way to think about
the total influence, right? That is one thing that I have not defined yet. Now I can define it. So we just talk about the influence of each individual variables. Then naturally you can define this to be the total influence. I stopped there to discuss a quantum setting because the definition of the total influence in the quantum setting depends on the choice of p. But this is not the case in the classical setting. So in the classical setting, the total influence is simply the sum of all these individual influences which, again, if you use free expansion, it has a better formulation. This is, recall that each ice, the influence of the ice variable is the sum of squares of free coefficients, where S contains this I. Now you sum over all the possible i's. What you get is essentially the Dirichlet form corresponding to the Laplacian operator. So in other words, this is equal to cardinality of the set S times square of the free coefficients. And this is the inner product of F and Laplacian or negative Laplacian of F with respect to the inner product induced by the uniform probability measure. So here, this negative delta is the discrete Laplacian, or the sum of di's. Each di is actually idempotent, so it's also sum of di squares, kind of the discrete analog Laplacian operator. That's why the L2 formulation is good. So in the quantum setting, this heavily depends on the choice of p. You can formally define this. The total influence with respect to the p is sum of this LP influence for all the individual i's. Well, you can always define this, but if you expect this to have some connection to the free expansion, you want this p to be 2, roughly. Okay.
And what is then the connection? Will you get the same formula? Or
yes. When you have this, when you have p to be equal to 2, this will be, let me write this A, L of A. So maybe let me write negative L. So firstly, you have this expression in terms of free coefficient. Secondly, it corresponds to the Dirichlet form with respect to the this L. L here is a generator of the depriving semigroup over this 2 to the n by 2 to the matrix algebra. what is this L? L here is given by sum of this little di. Okay, which here is minus L. Yes, you're right. Thank you. Which is again idempotent. So if you are familiar with the Laplacian, then there is a very fundamental inequality called Poincare inequality. So out of this, you can already say something about the total influence. Poincare inequality tells us that total influence have the lower bound, and we are going to improve this lower bound for some interesting applications. Okay. Any questions? So these are basically some preliminaries. Now I want to formulate the problem that we are interested in the classical setting. The first one concerns the degree. Second one concerns the influence. The first one have applications in the learning theory. Namely, you use a very deep harmonic analysis inequality to improve the sample complexity in the learning theory. Well, for the second problem, you use this analysis of these influences to prove the sharp threshold phenomenon for the random graphs. So we possibly will not have enough time to discuss these two topics. Let me present them to give you a flavor of the statements one by one, and let's see if we have time to discuss the details. So the first topic concerns the degree. Roughly, it is about learning low degree. Boolean function, or more in general, bounded functions from a small number of complexities I will explain this problem, this learning problem later. Let me first present what kind of analysis or harmonic analysis result we use here. And this is a so-called case theorem, usually named after Bohnen, Brunst, Hiller inequality. But their original inequality is for the circle group instead of the abelian group, instead of the discrete hypercubes here. And this inequality was proved first by Bly, and in 2001, and later extended by Defang, Mastero, and Paris in 2019. So what does this inequality say is the following. You fix your degree. You look at the functions on this n-dimensional Boolean cube. Then the following inequality holds. Okay, you assume the function to be of degree at most d. Then we have the following inequality. The little LP norm of your Fourier coefficient is bounded by the supreme norm of your function up to a constant independent dimension. Well, this constant can be chosen to be this sub-exponential constant c to the power square root of d log d, that is sub-exponential in d. Here c is a universal constant. Okay, it looks a little strange. And it may remind you of the Hausdorff-Young. Let me recall that Hausdorff-Young equality said the following. For p between 1 and 2, for p prime being its conjugative index, then LP prime norm of free coefficient of f is bounded by the LP norm of your function f. Here, this p here, the index on the right, is between 1 and 2. P prime here will be then from 2 to infinity. While here, for this inequality, what we'll call the BH inequality here, on the right-hand side, you have the L infinite norm of a function, while on the left-hand side, you have this index p that is strictly smaller than 2. To d over d plus 1 is strictly smaller than 2. So there are two important features of this inequality. First one, this exponent must be strictly smaller than 2, because otherwise, if you just consider the L2 norm, it will be L2 norm of your function. Since this is a probability measure space, it is automatically bounded by the L infinity norm. Then this inequality becomes trivial. So you must have this to be strictly smaller than 2. Secondly, this constant is independent of dimension. Otherwise, you can always bound it your little LP norm with your L2 norm, then you repeat the same argument. Then this comparison give you, when you compare little LP norm and L2 norm, you get a factor that depends on dimension. This inequality becomes trivial as well. So it's very important that this exponent is strictly smaller than 2, while this constant is independent of dimension. Any questions? This is a very good. This is a very good point. So this very strange constant of c to the power square root of d log d was best known in this case, and also in the case of a circle group. You repeat the same question for function defining on the circle group and for the product of n-dimensional circles. You have an analytic polynomial with bounded degree. You have the same inequality here that was first studied by Haonan, Boolean, and Hiller. And there, the best known result is this upper bound. And that's why, after known result by Bly in 2001, Define Master and Paris want to mimic the same upper bound in their paper. However, now it's not clear if this constant is sharp or not. But very recently, some people consider this problem using the completely bounded norm. And there you get optimal constant. What I'm saying is that you have the same polynomial, same functions, actually not necessarily multilinear ones. You can consider the function on the torus, so the function can be more general. You still have a little LP norm on the left-hand side. On the right-hand side, you replace by CB norm. There they have the constant 1, which is sharp. And this is kind of surprising because you don't have such beautiful result in the classical setting. Another sharp result that I know, also from the same paper by these authors, if you consider Boolean functions, which takes values in plus minus 1, they also obtain the sharp constant. The sharp constant, maybe I can write it here. Okay, maybe right here. So first sharp result says if you replace this L infinity norm by CB norm, when you replace by CB norm, the upper bound is actually larger, right? Yeah, I will define here in a second. The CB norm here is defined to be the supernorm. Now this is a polynomial, right? Your f here is a polynomial. It is, say, ai1, ik, xi1, xik. Oh, I think in their result they need this f to be homogeneous. So let's assume this to be homogeneous for a second. So I just rewrite the free expansion here using a more explicit formulation as a polynomial, okay? xi1, xi2, xid. Let's assume this is to be homogeneous. Then the CB norm is defined to be the supernorm. This time you replace these little xi's with capital Xi's, which are now matrices. Capital X are 1, capital X D operator norm, where all these x1, xn are contractions in some B of H, and you run over all this H. Okay, you take the arbitrary size of matrices, and you find the arbitrary n tuple of the contractions of these matrices, capital X1, capital Xn. Then you replace the variable here with this matrix variables. Then you take all this supernorm. With respect to this CB norm, they find this constant to be 1.
So is the D on the right the same as D on the left? So you have
this
homogeneous of degree D?
Yes, I assume this to be D-homogeneous. In a non-homogeneous case, they have an extra factor of square root of D plus 1. This is for all polynomials of degree at most D. They didn't say if this square root of D plus 1 is sharp or not, so I won't discuss it here.
When you say some people, can you figure things?
Yeah, so this. So this is kind of a quantum paper, I would say. Extend some result in the quantum setting, among which they also have some classical results. This is the second sharp result that I know. Here, if you restrict yourself to Boolean functions, you repeat the same question, you ask this inequality for function that is whose degree is bounded by D, so not necessarily homogeneous, then the same inequality holds with constant 2 to the power D minus 1 over D. Here I don't need to write down the L infinity norm because it's Boolean, so the L infinity norm is just a constant 1. and this 2 to the power d minus 1 over d, this is bounded by a universal constant 2, as you can see, is optimum. So in general, people conjecture, so some people conjecture that in general the constant should be polynomial in d, but some people even conjecture that the constant is just 2 independent of d because there is no counterexample. You run a lot of simulations in computers, but you don't have any counterexample. Okay, we may spend too much time in explaining this harmonic density inequality itself, but what is interesting is to benefit some learning algorithms significantly. So shall we have a break now, or first explain this learning algorithm and applications, and we have a break?
Carry on and explain the application.
Okay. So why do we care this inequality? If you look at the result in the history, it is about the convergence of Dirichlet series, having nothing to do with the learning stuff. But recently, people find this inequality quite useful in the, let's say, low degree learning. Okay, so the model is as follows. I want to learn the low degree Boolean functions. Let me give them a name. Again, I fix n, I fix degree, then I consider the class of function, which is essentially low degree Boolean functions, but actually the argument also works for bounded functions, so interval from 1 to 1. Okay, this is a class function that we want to learn. Again, recall that our goal is kind of to understand Boolean function with a small complexity. This time we are going to measure the complexity using degree. We want to understand it from its random samples. What does this mean? It means that I fix epsilon and delta very small. I consider the smallest capital N here. This N will depend on all these parameters, epsilon, delta, B, and N. This is my sample complexity. What it means is the smallest positive integer such that no matter which function you pick from this class of low degree, bounded low degree function, no matter which capital N, D random variables that say x1, x2, x capital N, ID random variable that are uniformly distributed over the Boolean cube, together with a random query that I know. For that I mean, as long as I know what x1, x2, xn is, I should also know the value of f of x1, f of xn. So capital N is the smallest positive integer such that, in this case, one can construct a function which depends on this random query, so it will be random as well. Let me call it h. H does not have to be Boolean or bounded, but this h is such that this h is closed to my unknown f with high probability. Okay, let me explain what it means. It means that I have a function, and you need to guess what this function is. I pick a function, say f of x, that is maybe 1 plus 2 x1, x3, or plus 4 times x2, x5, something like this, and you don't know what it is. Now the procedure is that, for example, we have 20 people here. This is a function that is defined on the 20-dimensional Boolean cube, and every time you need to give me a string uniformly, which means each of you just pick between +1 and -1 with equal probability. So you give me a string, say 1, 1, 1, 1, 1. I will return you the number of this function, the value of this function, whatever it is. This is the first round. Second round, you repeat the same thing independently. Each of you pick between +1 and -1 with equal probability. Maybe this time it's -1. -1, I will give you the value of this function. The question is, how many times do you need to construct a function from this information that is random, so that you construct this function with high probability is close to this function in L2 norm. Is this question clear? Okay, any ideas? So you see that we are using L2 norm, which is very often the case, and this is usually related to the harmonic analysis. And naively, the idea is as follows. By the way, this is a very bad example because the L2 norm is apparently bigger than 1, so it will not be bounded here anyway. So the point is, you don't construct the function directly, you construct its free coefficient. You construct a function, something that is close to 1, something that free coefficient is close to 2, something that is close to this 4. How can you do that? In general, if you have a free expansion, you want to approximate this unknown free coefficient. But from very beginning, we say how to recover this free expansion. It is the inner product of your function and the character. And this is computed in terms of value of f. So when you know enough number of the random values of your f, since they are all ID uniformly distributed with respect to the uniform distribution, the Chernoff bound tells you that as long as you know enough number of f, you should know this free coefficient with high probability. So what you will do is to construct this random free coefficient based on the random query that you know. So every time I tell you the number, the value of this f, as long as you know this capital N to be big enough, you know this alpha s is close to this f hat of s with high probability. Then to conclude, you want to estimate their L2 norm. So by Parseval identity, this will be the sum of little L2 sum of the free coefficient. F hat of s is a real free coefficient. Alpha of s is a random free coefficient that you constructed. You know with high probability, when n is big enough, capital N is big enough, this with high probability is very small. So this is equal to sum of small terms. Sum of small terms. How many small terms do you have? These are the number of the non-zero free coefficient, right? You don't have to approximate if you already know the free coefficient is equal to 0. How many non-zero free coefficients do you have? If you consider a function that is of low degree, then the number of the non-zero free coefficients is just the sum of this n choose k is smaller than or equal to d, and this is essentially of the order n to the d. So what you will do here in this summation part, you get order of n to the d times this small term. You want this to be at most epsilon. And if you repeat this idea, if you apply this idea to this learning problem, you get an answer which is 1993 result of Lineal, Mansu, and Nissan. They conclude with an upper bound of this capital N, which is of the order n to the d log of n. Here, this capital N depends on many variables. These 4 variables, here I will only concentrate on the dependence on the n dimension. When this little n goes to infinity, I hope that my number of random queries is not big enough. So I ignore the dependence on epsilon, delta, and d here. So in some sense, this is reasonable because you have this many of non-zero free coefficients, but so this was believed to be best possible for a long time until recently. Some people improved this to the order of n to the d minus 1 log of n, which is, let me write down the name of the authors, which is kind of a small improvement, but already surprising because you should have n to the d freedom of the non-zero free coefficients. These are the result of ideal. Okay, there are too many authors, so let me just briefly IRRRY. If you are interested in the reference, I can give you. But what is surprising is a result by Askenasis and Ivanisvili showing that actually log of n is enough. This polynomial dependence can be removed. Log of n is enough. Recall that you should have some kind of freedom of n to the d because you may have this number of non-zero free coefficient, but the conclusion is that log of n is enough. And actually this is optimal. The key is the inequality here. So this is kind of the state of the art of the first problem. If you are interested in the problem, we can give more details and extension to the quantum setting and some open problems. That will be the plan for the first topic. Okay, let me make a remark here that the sharp result that they obtained for Boolean functions, you may wonder if this can be extended to the quantum setting, though I have not introduced this inequality in the quantum setting yet. But the point is they use a very crucial fact for Boolean functions that have low degree. And this fact is as follows. If you have a Boolean function, you know the degree is already bounded by d, then its Fourier coefficient cannot be arbitrary real number, as we have seen here in the quantum example. And this must be discrete in the sense that it must be integer multiple of 2 to the power 1 minus d. We already see one example, quantum example A, that is certainly that is Boolean, quantum Boolean that has small degree, but the Fourier coefficients can be anything between 0 and 1. So this very simple factor fails. which makes this problem open in the quantum realm. Okay.
Sorry, this case meaning like all eigenvalues are in the quantum version. All eigenvalues are. So have we assumed that we're Hermitian unitary?
Yes, we say that A is quantum Boolean if it is self-adjoint and unitary. Yeah. So the second topic has an interesting application to the sharp threshold phenomenon of the random graphs. But the K theorem is an inequality about influences. Topic number 2, sharp threshold phenomenon in random graphs. Okay, let me first formulate the K theorem, mathematical K theorem. This is a so-called KKL, Kahan, Kale, and Lineal. This is a theorem about the influence. Recall that we discussed about the influence. We have this notion of the total influence, which is just the sum of the individual influences. I'm considering Boolean functions here. We know this is given by the usual form of the Laplacian or negative Laplacian here. Then by the Poincare inequality. Poincare inequality tells you that this has a lower bound. The lower bound is given by the variance of f, which means it is expectation of f square minus expectation of f square. Expectation here is with respect to the uniform probability measure. Okay. Then you can say that this has a lower bound, and very often people care about the Boolean function that is balanced. Balanced, what does balanced mean? So here you can think about the Boolean function as a voting scheme, like the majority function or dictatorship. You say this is balanced if it has expectation 0. In some sense, this voting is kind of fair. And in this case, this Poincare inequality tells you the total influence has a lower bound. This lower bound is exactly constant 1, because the Boolean function, so f squared is always equal to 1. Expectation is equal to 0. So total influence has a lower bound 1. As a consequence, the maximum of the individual influence is bounded from below by 1 over n. This is a very simple corollary, and you wonder if this is sharp or not. There were some conjectures, and there were some examples. Based on some examples, people conjecture that the lower bound should be log of n over n, up to universal constant. And this is a KKL theorem. KKL theorem says that there exists a universal constant such that for any dimension n, for any Boolean functions, say it is also balanced. So it means has mean 0. then the maximum of the individual influence is bounded from below by log n over n up to universal constant. And this is just the KKL theorem, okay? So this is another type of result that you want to understand the function with small complexity. This time the small complexity is given in terms of the influence. So when the influence is small, you want to understand whether if the total influence is small, is it possible that all the individual influences are small as well, of the order 1 over n? And the KKL theorem tells you that this is not the case. You can always find a small subgroup of people. If you somehow convince them to change their mind during the election, you may have a larger influence of the result. This is kind of one application, but what we want to discuss today is application to the sharp threshold phenomenon in random graphs. With this lower bound, you can observe the following thing. Let me remind you the definition of random graphs. Any questions about this KKL? Okay, random graphs. So let me fix the L-G graph, the G, V, P. Well, V here is my vertex set, say of cardinality M. P here is some real number ranging from 0 to 1. And this model says that you pick any pair, say x and y, in the vertex set, then x and y connected with the probability p. Okay, and for each pair, you choose all these pairs, and their connectedness with probability p is independent to each other. Okay, then you might be interested in some properties of the graphs. Since this p will change, say from 0 to 1, then the probability will change accordingly. Then, so for certain graph properties, say denoted by p, if you look at the single graph, if you look at the graph here in this random graph, it will depend on this p and m. We are interested in the behavior when this m goes to infinity. I will explain this graph property in general later. For the moment, you can think about the connectedness, which for this example, when p is equal to 0, then the graph is not connected at all. When p is equal to 1, it's connected. So there is some dynamics from 0 to 1. When p increases, how would this probability that this graph is connected, how it changes from highly non-connected to highly connected? So if you look at this picture, this is your p, okay? P will start from 0 to 1. Then this is the probability. The probability that this is a probability that your random graph has this probability. Okay, this is a very bad notation. Has this property P. So here you can take this P to be the connectedness. When P is equal to 1 to 0, your graph is not connected. So it starts from 0. When P is equal to 1, the graph is connected. So you can imagine how this picture looks like. It turns out that it will be something like this. Okay, this is not good. It might be something like this. Okay, so I'm not good at drawing this kind of pictures. The point is there is some critical point. Let's say PC. PC is a point where this probability is equal to 1/2. Okay. Critical point PC is defined to be the probability that your random graph has the property that is given, say 1/2. Then when you consider, say, connectedness, this kind of properties, there is this kind of phase transition. So around this point, before this point, your graph is very likely non-connected. After this point, your graph becomes very likely connected. And you want to measure how this transition rate looks like. And turns out that you can use this KKL theorem to prove that this is actually very sharp, very sharp. So we say that this property P, you can think of this P as this connectedness again. We say that the P has sharp, sharp threshold phenomenon if how to measure this? There are two ways. One way is that at this point you look at the derivative of this change of the probability. So if the derivative with respect to P at this point of the critical point PC of the probability that this G has this property P, actually this depends on M in general. The property here is actually a family of properties. So the probability, you look at the derivative of this probability at the critical point. If this is large compared to PC. Okay, sometimes actually people write it as a minimum of PC, and the QC, Q here is 1 minus P. This is the kind of the idea of this definition of sharp threshold phenomenon. Any questions? Okay, here is another maybe more rigorous definition here. You look at epsilon 1 minus epsilon. Here is your epsilon 1 epsilon, which corresponds to 2 points, say P0 and P1. Okay. Or equivalently, you pick any epsilon from 0 and 1/2, you look at the points P0 and P1, which will depend on epsilon, m, and p. So P0 is the value so the probability that G has GVP0 has probability, this is equal to epsilon, and for P1 it has probability 1 minus epsilon. Okay, then you compare this interval, the length of this interval, this is the interval around the critical point, and you look at this kind of change of rate over this from epsilon to 1 minus epsilon. Okay, so given this P0 and P1, we say that this property P has P1 here, that is given by 1 minus epsilon. He has so sharp threshold phenomenon if this limit, the limit of P1 minus P0 divided by this PC, everything here depends on the dimension m, vertex m. When m goes to infinity, this is equal to 0. This is equal to 0. Am I correct? This is equal to dot over BC. This is bound from 0. This might be equal to 0. Okay. And to be honest, I'm not very familiar with this part, with the second topic. I divided into two cases. You can also consider the curse. Threshold phenomenon if this quantity is bounded from 0. Okay. Any questions?
Sorry, what's the integral divided by PC or P0, please?
Oh, yes, it should be PC. Thank you.
Yeah. What's the integral divided by PT?
You mean this P1 minus P0?
Yeah, but you divide that by PT.
Yes. Oh, the intuition here is this change of a rate is large compared to this critical point. So you compare with PC. Okay, why do you compare with PC? Good question. If this PC is kind of fixed in the sense that it is a critical point that you have 1/2. So if PC is very small, it means you achieve 1/2 very early. If PC is very large, it means you change the value. So kind of this shape depends on where your PC is. This is kind of my understanding. I should say that I'm not an expert in this direction. So for this topic of the sharp threshold phenomenon, I actually don't even know how to formulate the right question in the quantum world. So what I can say is just to present the relevance between this harmonic analysis inequality and this problem.
Does anyone know what PC roughly is for the connectedness?
For many examples, for certain examples, PC is also equal to 1/2. But for connectedness, I think PC's, I actually forgot the exact, it's not 1/2. It might be some logarithmic of m, something like this. So, but I'm not quite sure about it. It's not 1/2. It's not 1/2.
So maybe we have to divide by if your critical threshold is itself racing towards 0, then it's meaningless to just compare P1 and P0 rescaling.
It's a half. What does the sharpness condition say?
If it is close?
If PC's half, say something like it's,
If PC is bounded away from 0, it's just saying that the intervals get smaller. But yeah, PC is getting smaller than. Doesn't say that.
Okay, that's why I want to present this topic that I'm not familiar with, just to open the discussion. Any other questions? So I don't have too much time. So in the rest, I will maybe present the general properties that have this sharp threshold phenomenon, okay? And try to connect with these analysis inequalities if time permits. So
If you could come back to the first topic, did you say anything about the quantum version of this, or?
okay, maybe we can have a vote now between these two. So either we come back to the first topic, or we continue discussion with the second topic. So our voting scheme is a majority instead of the dictatorship. So those who want to come back to the free analysis and the learning stuff, the first topic, maybe you can raise your hand. 1, 2, 3, 4, 5, 6. Okay, and those who prefer the second topic? 1, 2, 3. So the rest are just, we stop here and
Heard of plurality as stablest? Have you heard the conjecture?
which conjecture?
It's a extension of majority as stablest to like for 3 parties instead of 2.
Okay, this should be an open problem. You should name it somewhere. So let's come back to the first problem. I can give you a rough picture of what is known. We discussed the case of a Boolean group, just a very simple cyclic group of order 2. What was known before is actually on the torus. This was known by a lot of people. This was known already in 1931 by Haonan and Boolean and Hiller. That's why we mentioned it here from the very beginning. It's named after Haonan, Boolean, and Hiller when people consider the same inequality on the Boolean cubes. Then this is also the case with the algebras, in the sense that in the free analysis, the setup we started from the very beginning. You have the poly basis, you have the free expansion, you ask the same question because you have the notion of degree. In other words, the inequality here is that do you still have this inequality for matrices. On the left-hand side, you have LP norm of welfare coefficient. On the right-hand side, you have operating norm of a matrix. With this P to be still 2D over D plus 1, again, you assume this A is bounded of the degree is bounded by D. Okay, you want this constant to be still dimension-free, and the conjecture of this inequality was made after it was proved. Okay, some people prove it in a paper that was not public at that time, and we conjecture this is the case. They told us that immediately we put the paper in the archive, saying that we already solved the problem here. It was first solved by people from quantum computation, Suyuan Huang, Sitan Chen, and John Prisco. Their motivation is kind of similar to the class setting. They need to control the Fourier coefficient in a way that they need this P to be strictly smaller than 2 with this constant to be independent of dimension. So they have a very technical proof leading to a constant that is D to the power of D, essentially. And we find this proof kind of complicated and has a constant that is not as good as in the classical setting. So joined with Vollberg, we give another proof, simpler, and give a constant that is exponential in D. What we really proved is a reduction method, saying that you can reduce a problem on 2x2 matrix algebras to 2-point spaces, or to cyclic order 2. I will not have time to explain that, but then people ask what happens to k by k matrices. Instead of considering the so-called qubit system, you consider the so-called qubit system, where you have a generalization of polymatrices, the so-called Heisenberg-Weyl basis as a generalization of polymatrices, so that you can talk about the Fourier expansion, you can talk about Fourier analysis, where you have a very natural inequality there as a harmonic analysis problems. You also have the relevant learning problems, learning the quantum observables in the QD system. So all boils down to an inequality something like this, okay? And then the question is how to answer the question for k by k matrix algebras. Turns out that our previous method, reduction, works, but in a very involved way. This is joint work with Vollberg and Joe Slot here. We mix this direction works from k by k matrix algebras to something classical. This time not a 2-point space, not the cyclic group order 2, but the cyclic group of order k. Okay, this is a multiplicative group of order k with this omega to be the primitive root of the case, primitive root of the unit. Okay. So from here to here, from k by k matrix algebras to cyclic order k, this direction works. This is Slot. This direction works. Then the question is whether we have this inequality on classical cyclic order k or not. To be honest, I first considered this direction without knowing this. Okay, when I first see this inequality on the cyclic order 2, I ask myself the question of cyclic order k, because it's a very natural harmonic analysis problem, and then I tried and I didn't get anything. Then the story goes this direction, and I came back to the same problem. Luckily, with the same authors, we know that this inequality on this group is also true. So here the formulation is similar. You have a function this time on the n-fold product of the cyclic group of order k. you have the similar definition of the degree there here. You ask what happens to function with bounded degree. Do we still have this inequality or not? And the answer is yes. The constant will depend on this k, which is order of the group here. And actually more is true, but I will not explain here. So from two-point space, 2x2 matrix algebras, k by k matrix algebras, and cyclic group of order k. Any questions?
So here in this picture, in this quantum picture, do you
Yeah.
also have a version with the CB norm of some type?
Okay, CB norm. So the CB norm stuff is a bit. So this is CB norm. I wrote down their result, but their result is actually some CB version of functions living on torus. The difference, what is the difference? The difference is that now you consider function that is a multivariate polynomial. And this time, you don't have constraints on alphas in the sense that you don't just consider the multilinear polynomial. You are allowed to have a square term or third power term. So here the assumption is simply that this is bounded by D. Therefore, when you formulate these problems on in the CB version, your left-hand side is essentially the same, right? Your right-hand side, some constant. Right-hand side is this CB version. But let's see. Does this CB version see the structure of the group here? You replace this, no matter what real coefficients you have the supremum of operator norm of this polynomial with these classical variables, whether it is cyclic group or not, it always will be replaced by general contractions. So in some sense, this inequality is weaker because we are talking about a larger norm. So maybe it does not see the structure of the group anymore because it runs over all possible matrices with norm 1. And here don't see the structure of the group as well. So when you just restrict this inequality to function living on the cyclic group, you may just maybe you just recover the result directly. Okay, maybe I need to double check this, but I have a feeling that this does not rely on the group structure.
Can we use only the free product of the cyclic group?
Oh, this is a very good question. I don't know. This is my first answer. Second one is that I gave you this examples of group that you have this inequality. How about non-examples? Since you mentioned the free groups, free product, maybe let's just consider the free groups. Maybe you want to ask the same inequality in the free group setting. Fn here is a free group on n generators. You consider group from algebra. And the hard groups inequality tells you that if X is supported by X, say it is D-homogeneous, okay? D-homogeneous, then the operator norm is bounded by this D+1 times L2 norm, right? I forgot the constant should be something like this. And this is nothing but L2 norm of its free coefficient. Suppose that you have this inequality, BH inequality on free groups with constant independent of n. You will have a lower bound in terms of some constant times LP norm of your free coefficient with this P to be whatever it is bounded by 2, right? As a consequence, you can compare the little LP norm and the little L2 norm, because this direction you always have, because this is a little LP norm. So if you have this inequality on the free groups with dimension-free constant, you can compare little L2 norm with little LP norm with constant that is independent of dimension, and this is not going to happen as n goes to infinity, because the size will go to infinity. This one? This one.
Free group computation not for the torus, not for the finite cyclic group. Yes.
Right.
So if you have free product of copies of finite cyclic group, then you don't quite have.
Oh, that I don't know. I should say I don't know, and I always kind of viewing the cyclic group as a family of interpolating cyclic group order 2 and some kind of cyclic group order infinity. So, so yeah, I naively think that that would fail, but possibly I'm wrong.
Maybe just one more quick question. So, while you have this result for the cyclic group, so does
Yeah.
it also is it then easy to generalize it to any finite abelian group?
I mean the product of this group. I don't know, and I also don't know what kind of result you are expecting. You are expecting the n-fold product of the same abelian group, or with some G1 or G2. Okay.
You would probably start with G1 being Z2 and.
Okay.
We don't have this
Quick
written
answer, I
down,
don't
but I feel like.
If you use generalized approximation stuff, maybe yes. Maybe yes.
Direct product meaning the same thing as taking tensor power, it as a block. So actually this is the functional computation according to -1 bound.
So I'm saying that we out of this result, we just break down this n-fold product copy into maybe as copy of f as tensor product of t copies of this, right? Is that a question? Right. This as e to the power s, and is this your point? Write down the. So to extend the result from g to the power of s.
Yes.
Yes. This might be true. I think whenever you consider a problem of this kind, you need to define the notion of degree here with respect to this structure. If the definition of degree here is the same as defining the degree as a function on g to the n, I think the result reads the same. If you want to change the definition of degree here with respect to the structure, I don't know, maybe you can just compare the notion of degree here, because right-hand side is the same, always the supernorm of a function over this space, whatever structure you will decompose. So just compare the left-hand side. And this is a very interesting question, because when considering problem in k by k matrix algebras, some people simply ask, why don't consider k by k? You already know 2 by 2, 2 to the n by 2 to the n, just embed the k by k matrix into the 2 to the n by 2 to the n. Why don't you consider the k by k matrix algebras? So
Do you want to finish that?
yeah, I can finish. I already ran out of my time, but I think I will talk about some related things in next week or so, if everyone is interested, still some chance.
That's fine. Thank you very much.